So what we're going to do today is we're going to look at transactions, because that allows us to understand a lot of the mechanisms within the database management system. And particularly, we are going to try to understand how transaction support, concurrency control, and recovery services work together to give us the consistency that we require in a database, how they enable us to maintain consistent data in the database. And so what we need to do is understand how concurrency control works, the purpose of database recovery, and also transactions, how they work, what is the importance of transactions. And all of that is covered in Connolly and Beck chapter 22, which you have to read, or there is some additional reading there if you want to know more. So the first thing that we're going to look at is transactions. So we have to understand this concept of a transaction, and we've talked about this before in the lectures. We've kind of come across it in the context of SQL. When we're talking about a transaction, what we're talking about is a sequence of operations, which are read or write operations, grouped to form a database access. And they are a logical unit of work. What happens with that transaction is that all of the operations that are within the transaction should either happen and be committed to a stable storage, or they should be rolled back. And if we have that, then we have consistency, because the database should be consistent before the transaction starts its operations. And if we group things according to how they should be logically, then it should also be consistent after the transaction executes. Or if the transaction fails, we should be able to roll it to the beginning and go back to the consistent state that existed before the transaction started. So that is what we are going to look for. So to preserve the integrity of the database, what we are looking for is atomic transactions, i.e. they are all like a block of operations that work as one unit, one logical unit. So they're either going to completely execute or not at all. And it's going to be the DBMS who has to guarantee this atomicity. So it has to make sure that the transactions are going to either execute or not execute. So how is it going to do that? That's what we're going to try to explore through the course of this lecture. And why do we actually want to have these transactions? Well, there are some advantages, because if you are a developer and you're working with a database, and the DBMS deals with a transaction, a lot of the complexity of writing the application is taken away from you. You do not need to worry about concurrency. Concurrency, as we will see through the lecture, is a difficult thing. When you have concurrent operations, there can be a lot of problems with the data and the consistency of the data. But if the DBMS is managing concurrency through the transaction operation, then you don't need to worry about it, because it's going to be managed for you. So it takes away, if you're developing an application, the worry about concurrent access to the database. It is also going to deal with things like partially completed transactions if there is a system failure. So what happens if the transaction is partially completed and then the system fails? The DBMS will ensure that the transaction is rolled back to a point of consistency, or redone to a point of consistency. So again, you don't have to worry about system failures, because the database management system will deal with that in terms of transactions. And it also gives you a way as a user to undo a particular transaction. So you can roll back a transaction if you wish, because there is an error. So if you use a DBMS, there is a lot of complexity, as we will see, involved in operating a DBMS. More, especially when you talk about concurrent access, than you will think. But a lot of that is going to be handled by the DBMS itself. So you don't have to worry about it as a person who interacts with the DBMS either through application or through the interactive SQL interface. You're not going to worry about that. So we might have simple transactions, we might have more complex transactions, or we could have transactions that span a very large number of operations, depending on what we're doing. So one transaction on one side, transaction in there, and we're going to use this notation, because transactions are made up of mostly of read and write operations, and occasionally other operations. So there we have a transaction which is taking our database, the parts database, and is changing the weight. So it's updating the weight within the parts table. So it needs to read, first of all, an item, which is the weight for a given part number. So that requires a read operation. Once I have that value, I want to take that weight and multiply it by 2.2. So I want to update it. And then I want to write it back to the stable storage. So those three things together are my one transaction. I read the value, I update the value, I write the value. I might have another more complex transaction in the other side where I want to delete a supplier. But before I do that, I want to update all of the shipments that are associated with that supplier to a new supplier. In that way, I can maintain referential integrity. Remember that referential integrity is what? What is referential integrity? Do we remember? Do you remember what is referential integrity? It is one of the constraints that says what?
All the tables should have the same attributes to do some action on it.
All the tables should have the same attributes?
Yeah.
Referential integrity, not quite. What does the referential integrity says?
Every foreign key must be referenced to a primary key and another table.
Yeah. If we have a foreign key, that must contain a valid reference to another candidate key, possibly the primary key, or be wholly null. And that maintains the whole model correct, because when we have objects that link together via this foreign key mechanism, we maintain those references valid. So if we want to maintain referential integrity, and we have a supplier that supplies shipments, if we delete the supplier, we got to think, what do we do with the shipments? If we delete the supplier and do nothing, we'll end up with shipments that are associated with no valid supplier. So that will break referential integrity. So one of the things that we could do is to make sure that all of the shipments associated with the supplier that we want to delete are given to a different supplier. So that transaction might do that. I want to delete some S number, some supplier with an S number equal to X, and for all shipment records, I want to do the following. I want to read the part number associated with the supplier number. If the supplier number is the one I'm deleting, then I want to update that supplier number. So then I make S number some new supplier number, and then I write that to a stable storage, and then I'm done. So I am going to update every single shipment. And I might want all of that to be packaged as a transaction, so that it all executes together. Because if I'm in a situation where I delete the supplier, but I don't update the shipments, I have an inconsistent database. And this is what I'm trying to avoid, having inconsistent states in my database. So if I do it as a transaction, I can guarantee that my database will be consistent before and after the transaction executes. So when I have a transaction executing, it begins. So it might begin with a begin transaction statement, which says to the database, I am beginning a transaction. All of the SQL statements then until I either commit or roll back are part of this transaction. So it's going to be active at that point until there is something that ends that transaction. It could be a commit statement, it could be a rollback statement, it could be a system failure. All of those things could end the transaction. Now, while the transaction is active, some of the operations in it might have been done, and I have a partially committed transaction, but it hasn't been fully committed because it hasn't yet been written to the stable storage. From that, I could either commit the transaction, so I write all the changes to stable storage. My transaction is then committed, and it has moved from consistent state to consistent state. Or it could fail. Something could fail within the transaction because of concurrency, because of a system failure, in which case it needs to then be aborted. So we go back to the beginning before the transaction took place. So to guarantee that transactions are going to move us from one consistent state to another, what we have to do is we have to guarantee that they have certain properties, which are called the active properties of the transaction. And this quite often has been an exam question. So it's worth knowing what these properties are, because it is frequently asked in the context of transactions. One of them is that they have to be atomic. So ACID comes for atomic, consistent, isolated, and durable. So those are the properties that a transaction must have, that the DBMS must guarantee. One of them is atomic. So that means that it either completes or fails as one unit. All of the operations in it are seen as one atomic component. It completes or it fails. It is all or it is nothing. You don't partially complete a transaction. You cannot do that. It has to be consistent. That means that it transforms the database from one consistent state to another. Whatever is packaged in the transaction must move the database from one consistent state to another consistent state. So you shouldn't have transactions that leave the database in an inconsistent state. So for example, you shouldn't have a transaction that just deletes the supplier without assigning the shipments to a new supplier, because that would be inconsistent. The other thing that they need to be is isolated, and that means that they don't interfere with one another. And we will see cases of where transactions might interfere with other transactions. This might happen if a transaction makes some changes, which are partial changes, and they are visible to other transactions. So if the transaction is receiving partial results, it might end up in an inconsistent state. So we don't like that. We want them to be isolated. And finally, they need to be durable. The results of the transactions are not lost, even if we have a failure. So even in the presence of a failure, we must be able to recover from that, and we must be able to recover our transaction. So those are the 4 properties that a transaction must have. And if we look back over lecture 1, I think, when we first met, and we were young and not so tired as we are now, we looked at the database architecture, and we looked at the diagram like this, a more complex diagram because it had the rest of the database management system in it. But we know that there was a transaction manager and a scheduler, and there was the data manager, which had the buffer manager and the recovery manager, and that interacted with the file manager, which through access methods and using the system buffers will then get the data from the database. So the transaction manager is going to be coordinating the transactions. There are going to be multiple transactions executing at once, because we're thinking about a concurrent system where many users can be accessing the same data. So they might all be giving different transactions at one time. So for example, if you're using your bank account, you might be withdrawing money where your boss is putting your salary. You don't want these things to have an ill effect. You don't want to lose your salary because at the same time you took £10 out, and the only thing that is reflected is the £10 that you took out and not the 1,000 that your boss put into it. So we are operating in concurrent environment. The transaction manager is going to be managing that concurrency, and is going to use the scheduler for that. The scheduler, which is also called the log manager, is going to control the order in which transactions and operation within transactions execute to give you maximum concurrency. And we will see how log mechanism works to allow you to have maximum concurrency. And we also have the issue of recovery. What happens in the presence of a failure of any kind? A disk failure, memory failure, a fire, whatever. For that we need the recovery manager, which is going to look at failure while we are executing a transaction, and it has to recover from that. So it has to recover to put the database in a consistent stage. And then we have the buffer manager, which is going to be transferring the data to and from main memory. So while we are running the database, we might have certain data in main memory, but we need to send it to secondary storage for it to be permanently stored. So the buffer manager is going to be involved in that. So that is our database architecture that we looked at when we started. So why do we want to have concurrency? We want to have concurrency because these days we do not want just one user accessing the database. Most applications require a number of users to be able to access the database at the same time, but without ill effects for one another. If you, again, are booking a flight with Ryanair or EasyJet or any of these companies with hundreds of people are maybe looking at the same flight, you want to be able to, if there is just one seat left in the plane and you book it, you don't want to turn up and find out that 10 other people also at the same time saw the same seat and managed to book it, and only one of you can get in the plane. You want to make sure that when you get there, if you were the one that booked the last seat, it wasn't available to everybody else. But maybe if it's a busy period, a lot of people are looking at that at the same time. So how do you manage that? Now, a naive solution to trying to have concurrency will be to say all of the transactions are going to be in a single string. And therefore, we are going to execute them serially, one after another. If I do that, when I look at my flight, I might be the only person to access that. So that is going to be not ideal in a real system. Because the moment I started looking at my flight, it gets locked onto me. Nobody else has access to that system. So that will not be a very practical solution. There will be, in that case, no concurrent execution. I will be in control of that system until my transaction finishes. Once I finish, either I book it or I don't, then someone else might be able to see it. So that might not be exactly how we want to operate. It's not going to be very practical, where we have a lot of people trying to operate on one single database. So we want to allow as much concurrency as possible. But we have a number of problems that can occur for concurrent operation in a system. The first problem that can occur is what they call the lost update, which is the one that I explained to you with the bank. Let's say that we have somebody is going to their bank, they read their balance, which in this case is X, and then they take some money out, £30 out of their account. So their balance becomes X minus 30. At the very same time, concurrently, someone else, the bank administrator, is also accessing the account. And is going to read the value of X, which might be the original value of X. Then it will read another value, maybe the salary. Then it's going to make X equal to X plus Y. So maybe whatever my value of X, if I initially had 100, this would have left me a 70. But now here I read 100, and then I'm going to add 1,000, which is my salary. So here X should become 1,000 plus 100. And then I write the value of X. But this then hasn't written the value of X now, does it now? So this update is lost. The only thing that is reflected in my balance is the fact that I took £30 out, but not that somebody else at the same time put £1,000 in. So that is what we will call a loss update. And it's one of the problems that you encounter when you're doing concurrency access to a database. So you want to prevent that from happening. You want to prevent the lost update problem. So if you wanted to see it in kind of semi-SQL, what will happen is my first transaction might be saying like select balance as all balance from current account, where account name is equal to Joe. Then maybe does some checking to make sure that there is enough money to pay a particular bill. And then it updates the current account, set balance to on balance minus phone bill, let's say. So I'm taking £30 out from my phone bill or whatever. At the same time, the other concurrent transaction is saying select balance as all balance from current account, where account name is equal to Joe, so it reads the same original value. Then select salary from something where employee number is equal to Joe, and then update current accounts and balance equal to all balance plus salary. But because this update executes in time slightly after, it gets overwritten. So I lose my update of the salary because there is concurrent execution, which is not working well. There is a loss update problem. Can we all understand that? So we want to avoid that problem. Another problem that might occur when we have concurrent execution is called the dirty read problem. And this happens where we have two transactions executing concurrently. T1 updates a record, and the second transaction reads that record. So it takes the value that T1 has just updated. But then T1 hasn't quite finished, so it aborts. So in fact, the value that T2 read is an incorrect value because it never materialized into storage. So now T2 is in an inconsistent state because it has read a dirty value, a value that hasn't been committed. The first transaction has aborted, but the second transaction has seen data, what we call dirty data, from the first transaction. And that is going to have, again, an inconsistent state, which we do not want. So for example, we have a nurse which is recording a dose of 2,500 milligrams of paracetamol, not a very good dose because I think that might kill you, to be given every 4 hours. And then a report generating transaction reads that value, and includes it in the report. But by this time, the nurse realizes the error because it was a high dose, too high a dose, so she corrects it, aborts that, and doesn't have that value in. So the second transaction, the report, is going to have inconsistent data because it read data that wasn't fully committed. It was in fact erroneous data because it's been reading dirty data. So this is what we call a dirty read problem. So if I wanted to look at it in SQL or pseudo SQL, then I will have something like insert into medication, patient ID, drug, quantity, and frequency, and I'll have whatever values plus the 2,500 grams. Then the application might ask for confirmation that the record is correct, but meanwhile the drug audit comes and takes the data that is not fully committed. So we select patient ID, drug dose, equal to 24 divided by frequency hours times the quantity of the drug, and then the nurse now realizes the error in the first, aborts that transaction, but the second has already operated on an incorrect value. It has done what we call a dirty read, so it has inconsistent data. So that is going to be also a problem. A similar problem is what we call an unrepeatable read. So again here we have two transactions processing together. The first one, T1, reads a record and then does some processing, and in this time T2 comes and updates the record. If T1 then tries to read the record again, it's not going to find the same value as he found in the first time. So this is what we call an inconsistent read. A transaction reads a value twice, but in between something has changed that value. So it produces an inconsistent read. And that again gives us an inconsistent state. So if we use the previous example, the nurse might realize the mistake, and instead of aborting the transaction, he enters a different value, the correct value, maybe 25 grams. So the report generator might have read an original value, then he has to reread that value again, but when he reads it again, he finds a different value. That is an inconsistent read. So that is another problem that is going to occur when we have concurrent access, or might occur. So if we look at it in terms of SQL, we might have something like insert into medication, patient ID, drug quantity, etc., and the values as we were doing before with the 2,500 dose, which is incorrect. Then an audit comes along, an audit transaction, and selects some information, including that dose, which is incorrect. Now the nurse realizes the error, and instead of just aborting the transaction, corrects it to be 25. So she goes, update medication, set quantity to 250, or 25, no, 250. And what happens is, when the audit then come to do a check on abnormal values, because he realized the first value that he read it was very high, so maybe the audit goes back to reread the data, make sure that the abnormal value is there. It is no longer there because it has been changed by the other transaction. So the value that triggered the alert now doesn't exist. This is what we call an inconsistent read. You read one value, something has changed, and you come to read it again, it isn't there anymore, it's changed. So it's an inconsistent read. And then the final problem that we might have is what they call a phantom. And that is where we have things that should be packages of one transaction logically are not. They are divided. And therefore, because things are not properly packaged into a transaction, we end up again with inconsistent data. So in this case, let's say, for example, that we have a hospital that is booking beds. And a transaction, one, first lists the patient's names for each ward. So I get a list of all of the patients that I have in a particular ward. And then it's going to compute the total number of free beds, given the patients that I have. So I know the total number of beds. I now have a list of the patients that I have, and I can compute how many free beds I have. And there is another transaction which is going to book a patient into a free bed. So these transactions are operating concurrently. Now, T1i and T1 T1i and T1ii really belong together as a transaction. Because to be in a consistent state, they should be packaged together as one transaction. If we separate them into two, then we could have an ordered operation where T1i executes, then T1 executes, and then T1ii executes. And that will leave us with inconsistent data, because the first one is going to look at the total number of beds. The second one, so the first one is going to look at the total number of patients. Then we're going to book a patient into a free bed. And then we're going to look at the total number of free beds. So there will be an inconsistency between the list of patients and the number of free beds, because in between, someone else has booked patient. So because we have not packaged things correctly, we end up with what we call a phantom grid. So if I wanted to look at it in terms of SQL, I could have something like select pname, word name from inpatient, order by word name and pname. So I'm getting a list of patients there, and that reflects some of the patients that are in my database at the time. Then this other transaction comes and executes because I haven't packaged that in a transaction together with the last bit. So I have insert into inpatient, pname, wname, date and condition, values, whatever. So I get the new patient into the database. And then the second part of what should be one transaction executes. So now I come and select the word name and then calculate the free number of beds from the word, where the word is some word name. So what happens is the list does not match the number of beds, because in between some patient has been booked in. So transactions that should have been made into one logical unit, the first in the lat, haven't, and therefore I have again an inconsistent state. So all of these things are the problems that you have when you work with concurrent access. If you were writing your own programs without the database management system, you will have to deal with this concurrency. But if you use a database management system, the database management system will deal with the concurrency of access to the database, and you won't have to worry about it, because it will be done for you by the DBMS. So the key to solving the problems that we have seen, whether it is a data grid or a phantom, etc., is to derive a transaction execution order which is equivalent to a serial schedule. And a serial schedule is one in which we execute one transaction after another in some serial order. So if we have a concurrent execution that is equivalent to that, because if we execute one transaction after another, we will have none of those problems. So provided that we can work out a concurrent execution of the operations in a transaction that is equivalent to a serial execution, then I should be okay. And that is what we call a serializable schedule. That is going to be sufficient to avoid the conflicts that I have said. So if I have a serializable schedule, then none of the problems that might come with concurrency will allow. And it's going to allow us concurrency, maximum concurrency, which is what we want to have. We want to execute things as if they were serially executed, one after another, but we want to do that managing maximum concurrency, allowing users as much access as possible to the resources at the same time, provided that doesn't have any ill effects on the database. So a non-serial schedule is going to be correct if it produces the same result as some serial execution. So as long as my execution of things in parallel produces the same result as execution transaction 1 and then transaction 3 and then transaction 2 in some order, then this is going to be correct. So in order to understand how we do that, we need to understand some definitions. The first thing that we are going to think about, because we're going to start thinking about how we might log particular items, etc., is the concept of a granule. And this is going to be a unit of data that is individually controlled by the concurrency system. So it's the unit of data that the concurrency system is going to use. Now, the granularity could be a page of data, because data is put together in pages. So it could be that the granularity that we use in a concurrency system is a page. It could be an individual tuple, a single record, or it could be a whole entire file. Obviously, the smaller the granularity, the more concurrency we might allow. Because if I use as granularity a whole entire file, while that is locked by a particular transaction, no other transaction will be able to access that. If I only lock one individual tuple, the rest of the tuples will be available. So having a smaller granularity has some advantages in that we can have more concurrent access to the data. But it also becomes more difficult to manage because there's going to be more contentions on all of the different items. So most commercial systems are going to give you a variety of granularity, from being able to use a tuple to a page to an entire file. And some of them will have changed the granularity dynamically. So they might start locking individual tuples, but if the transaction is accessing a lot of data, they might go then to lock an entire page or an entire file. So it can be something that is upgraded through the process dynamically to allow the best performance. As well as the granules, the next thing that we have is the action. And that is the unit of processing that is indivisible from the DBMS perspective. So generally, when we're talking about the actions for the granules, we're either talking about if the granule is a page, we're going to have actions which are going to be read a page or write a page. If it's a tuple, it will be read a tuple or write a tuple. So these are the kind of actions that we are looking at as indivisible. And then, once we have defined an action, we have to think about what are permutable actions. So two actions are permutable if every execution of the first action, AI, followed by AJ, is going to give you the same results as the execution of AJ followed by AI. So that makes them permutable. It doesn't matter how I execute them, I get the same results. If I have actions on different granules, they're always permutable. So if this is going to access this page and this is going to access a different page, that is always going to be permutable. It doesn't matter if I read this first and then that first. It doesn't matter if I write this first and then this later. Actions on different granules are always permutable. If I am going to look at actions on the same granule, so I have two transactions that are accessing the same tuple or the same file or whatever, or the same page, then we have to think about what kind of actions do I have. Two read actions are always permutable. It doesn't matter whether this transaction reads this value first and then this transaction reads the value, or this one reads the value and then this one reads the value. That is permutable. Even if they're reading the same value, the order isn't going to change the result. If I have read-write, they are not permutable, because there is a difference between one transaction reading the value and one writing the value. It's not the same as if the first one writes it and then reads it. So read-write are not permutable. The results are going to change depending on whether you read first or you write first. Equally, write-write are not permutable, because one write is going to nullify the effect of the second write. So when I'm thinking about what is permutable, if they're in different granules, they are permutable. If they're in the same granule, what is permutable is two reductions. So read-write and write-write are non-permutable. So then we have a transaction. And a transaction is going to be a sequence of actions, which could be reads or writes, for a given user that respects the database consistency. We have said the transaction has to take the database from one consistent state to another. So it always has to respect the consistency of the database. The database must be consistent before the transaction executes, and it must move to another consistent state after the transaction executes. So that is what we're looking for. During the execution of the transaction, there might be inconsistency in the database. So while I'm executing the transaction, there might be inconsistent states, but before and after, I have a consistent state. And a schedule, in that context, is a sequence of actions that is constructed by merging the actions of the set of transactions. So I have transaction 1 and transaction 2. Transaction 1 might read something, update it, write something. Transaction 2 might be reading the same item, updating it, writing it, reading another item. So what I have to do in the schedule is I have to find the way to interleave those operations. They should respect the order of the transaction. So within a transaction, the read comes first, then the update, then the write. So that has to be respected by the schedule. But I can interleave the operations of the two transactions, providing the result I get at the end is the same as if I had executed one transaction first and then the other. So that takes us then to a serializable schedule. And that is going to be a schedule that allows a set of transactions to execute in some order such that the effects are equivalent to executing them in a serial order, one after another. So what I'm looking for is how do I interleave the operation of two transactions so that the end effect is the same as if I've done one first and then the other. So in the case of my bank account, I might be first updating the balance by taking away £30, and then updating the balance by increasing £1,000. If they execute serially, I read £100, I take away 30, I end up with 70. I then come and take 1,000, put 1,000 in, so I end up with 1,070. If I did it the other way, I could read £100, and because it doesn't matter which way, as long as the result is correct, with respect to executing them serially. So I could start with 100, update by 1,000, then I have 1,100, then take away 30, and then I end up with 1,070. The idea is that if I want to produce a serializable schedule, my operations within the two transactions have to be interleaved in a way that the end result is going to be the same as if I execute one transaction serially and then the other. Do we all get that? Yes? No? Yes, yes, yes. So you understand the difference between executing them serially, one after another, or executing them concurrently. And what I'm looking for is concurrent execution that gives me the same result as serial execution. And what I can have with transactions is I can have a series of consistency levels. So level 0 consistency, which is the lowest level of consistency, means that the transaction is not going to overwrite other transactions' dirty data. So if a transaction has modified an item, another transaction is not able to write that dirty data. That is not going to give me a recoverable transaction because the transaction might have interactions with the external world that cannot be undone. So it's the lower level of consistency. If I want better consistency, level 1 consistency, I need level 0, i.e. I need a transaction that cannot overwrite the dirty data of foreign transactions, but at the same time, I want the transaction that doesn't make any of its updates visible to others either. So that is going to be the minimum consistent requirement which allows a transaction to be recovered in the event of a system failure. So we want to guarantee at least this level 1 consistency. So a transaction doesn't overwrite the dirty data of other transactions, but it doesn't make its updates visible to other transactions either. I can have a higher level of consistency. Level 2, which is going to be level 1, so the two conditions before are going to apply, but in this case, the transaction doesn't either read other transactions' dirty data. So that is a level 2 consistency. It doesn't write over other transactions' dirty data, it doesn't allow other transactions to read its dirty data, and it doesn't read other transactions' dirty data. And finally, the level 3 consistency is all of that, plus the transaction can perform consistent reads. So that avoids that problem of the inconsistent read states. Now the transaction can update data read by T before T has committed. So in the last level of consistency, I will avoid all of the problems, the phantom read, the unrepeatable read, etc.